Okay, so today I will be showing you problem 1.3 number 9, the first three parts. We're not going to do the fourth part. Okay, so what is essentially the problem? The problem first proposes a condition that is called a Dor space that says that a topological space of a set X and a topology acting on that set is said to be a Dor space if every subset of X is either an open set or a closed set or both, meaning a clopin set. So the first question just asks if a discrete space is a Dor space. Now, what is defined as a discrete space? A discrete space takes a discrete topology, let's call it tau 1, that includes the set X, the empty set, and every subset of X. That is the definition of a discrete topology. Now, if tau 1 includes X, the empty set, and every subset of X, then every subset is an open set because it is included within the topology. And by definition, if every subset of X is an open set, this can be considered a Dor space within this topological space. So the first one's pretty straightforward. Since all the sets are in the topological space with tau 1, the space is a Dor space. Now, the second question asks if an indiscrete space can be a Dor space. Now, this is a little bit more tricky because indiscrete topology, let's call it tau 2, only includes the set X and the empty set. And now, although these two are clopin to each other, meaning that the complement set of X is the empty set and the complement set of the empty set is X, the subsets of X, which are included in the topological space, are not part of the topology tau 2. So we're going to prove it by using a counterexample. Take this a subset of X, call it S, in which S is just a subset including 2. Then S is not open because it doesn't belong to tau 2, and it's not closed either because remember from the definition, a subset could be part of the Dor space if it's closed as well. But it's not closed because its complement is also not part of tau 2 because its complement would be all the other elements except 2 that belong to X, but not X itself. So it is not included in the topological space. So the topological space X and tau 2, as we defined it, would not be a Dor space because it doesn't include neither the open set of S equaling 2 nor the closed complement set. None of those sets are part of the topological space. Now for the most interesting question of the problem, number 3, which asks if X is an infinite set and a topology on X, let's call it tau 3, is a finite closed topology, is the topological space with X and tau 3 a Dor space? Now, first of all, this means that if the finite closed sets are part of the topology, that means that the infinite open sets are the open sets in the topology. So we're going to use a little lemma, a little fact to help us here, and is to understand that every infinite set X has a subset S whose complement is and let's say S is infinite because X is infinite. Then it has a complement S where both S and its complement are infinite. That is a fact. We're not going to prove it in this video, but it is going to help us with the proof for this. So now, by counterexample, to show you sort of what I mean, let X, our infinite set, be the natural numbers. Now, if you take the subset of the odd numbers, which is also an infinite set, but it's a subset of the natural numbers, then its complement set would be the even numbers, which is also infinite. So both sets would be subsets of X, and both sets would be the complements of each other, and both sets are infinite. And the definition stated in the question says that if you have an open infinite set, its closed set needs to be finite. So for example, a set that would be finite that would work in this scenario would be, for example, the set containing 2 in the natural numbers, and then its complement that would be open would be the range going from 2 without including it to infinity union with 1. That would be its open complement. But that is not the only case that can happen with subsets of X. And we need to include all subsets of X because they're part of the topological space. So by this counterexample, we show that you can always find a set S and a complement set of that S that are both infinite if they are subsets of another infinite set X. Hence, this would not be a Dor space because you can have sets that are subsets of our initial infinite set that are open but don't have a finite closed complement set. So the topological space would not be a Dor space. Thank you.